you for your introduction, Hans. So, hello to everyone. So, I'm going, in fact, to give you a presentation about EPM for solid state forming processes, dealing especially with all aspects related to modeling and design of these processes. Huh? Okay. So, next slide. Okay. I'm just, okay. Okay. I'm just, good. So the webinar objectives, will be regarding the modeling of electromagnetic couplings in some solid state manufacturing processes. Get information about which kind of modeling technique can be used. I will give a few examples. And try to understand better how modeling can bring an essential contribution to designing these processes. So, first of all, if we want to speak about some solid-state manufacturing processes involving EPM, there are, of course, many of them. We can give a few examples. For instance, induction mass heating, in which you are going, in fact, to have a coupled electromagnetism with heat transfer. You have induction heat treatment processes, in which the electromagnetism and heat transfer will also be coupled with metallurgy and solid mechanics, because you can, of course, have some metallurgical transformation. You can have some distortions due to the process, which can take place. You have other processes which are becoming increasingly popular, which are magnetic pulse forming processes, in which, in fact, you have a strong coupling between electromagnetism and solid mechanics. So in induction heating processes, as you know, you have a part which is being heated by a cylinder through which, in fact, runs an alternative current. And so you generate induced currents in the workpiece. And so if you do induction mass heating, you are going to work with low to medium frequency frequencies, so for heating. And so the industrial goals normally you aim to achieve are either to achieve uniform heating, also in some cases to try to control temperature heating rate, also to reach a given temperature field before you are going, for instance, to start a forging or an extrusion process. If we speak about induction heat treatment processes, in those processes, in fact, you have induction surface heating, so at a quite high frequency, which is then followed by quenching, either with water or oil. And so in those cases, in fact, the main goals are to try to control the microstructure, to control the hardness. It can be also to try to minimize distortions, especially as parts are getting, I would say, thinner and thinner, to try to reduce their weight, and so increasingly you have problems of distortions which appear when you use induction heat treatment. You also have magnetic pulse forming processes, and so here, in fact, I show, in fact, a system, in fact, of magnetic pulse forming, where, in fact, you have a generator, in fact, which is made of several capacities, and which is you are going to discharge over a very short period of time the voltage, in fact, inside the coil. And so those processes, as you can see in the bottom of the slide, take place over about 100 to 100 microseconds with quite high, in fact, current intensities. And so the principle for those processes, in fact, is based on the Lorentz force. Since, in fact, you are going to discharge a current in an inductor, and you are going to get, in fact, some eddy currents coupled with a magnetic field. And so the coupling of both will give a rise, in fact, to Lorentz forces. And so then you can form, for instance, the part. And those processes are also used, in fact, but in other kind of applications. It's with in water. In fact, when you discharge current between two electrodes in the water, and then you can also get very strong dynamic solicitations, which can also enable, in fact, to form some parts which would not be, I would say, formable by classical methods. Okay, and so with magnetic pulse forming are quite interesting because in fact, you have an elimination of the elastic spring back, which is quite interesting compared to, I would say, deep drawing processes. And it can also be applied, for instance, for cold welding, in order, in fact, to be able to weld materials which are not weldable by other classical welding processes. So now I'm going to say a few words about the physical models which we use for solid-state forming processes. So in fact, in those processes, one specificity is that you have different kind of multiphysics couplings which are being involved. Of course, some may be neglected, others not. If you have a look, in fact, at the different physics, in fact, which appear, in fact, on the display, so you have, of course, electromagnetism with EM fields and induced currents. You have temperature because, of course, you have heat transfer problem. You have on the bottom left, in fact, phase changes due to metallurgical transformation, which can take place especially during heat treatment processes. And you also have stress and strains, which can take place due, for instance, to the solid mechanics and to the pressures which are being, in fact, seen by the parts. And so, of course, you can have different kind of couplings, and of course, those couplings will impact the numerical modeling strategies which you will use afterwards for these. So as we said, in fact, so mainly when we speak about EPM for solid-state forming processes, we have four main fields of physics which appear: electromagnetism, heat transfer, solid mechanics, and metallurgy. So speaking about the models, so for the electromagnetic models, in fact, we've got, they are classically based, of course, on the Maxwell equations, where, in fact, you have the classical Maxwell equation, the classical equation relating the curl of the magnetic field to the current density. You have the induction, in fact, law, where, in fact, variation of the magnetic field will give rise to an electric field, so the minus the curl of E, which is equal to dB over dt, and the divergence of the magnetic field, of course, which is equal to 0. But you also have to add to these equations, you have, in fact, to add what we call the electromagnetic constitutive laws, which, in fact, besides the Maxwell equation, those are the laws which are going to take into account the material parameters. You of course, you have the Ohm law, in fact, which relates the current density to the electric field through the sigma, which is the electrical conductivity, which can be temperature dependent. And you also have mu, the magnetic permeability, which can be temperature and magnetic field dependent. Temperature because, of course, you know that if you go above the Curie temperature, you drop to 1 for the magnetic permeability. And also it can depend on the magnetic field. And one thing I want to insist on is that, in fact, getting access to those data is not always very obvious. Even the temperature dependence of electrical conductivity can be sometimes quite difficult to get. And you can see when you do some modeling of EPM solid-state forming processes that you can really get very different results with some slight changes in this data. And so it's quite important, in fact, to be able to have good, accurate data. So regarding the electromagnetic models, you have different field formulations which can be used, AV formulation, T omega, and for all those formulations, in fact, are meant, in fact, to try to synthesize, get a synthesis of the Maxwell equations in some more, I would say, exploitable way for the numerical modeling. So for instance, the AV with a magnetic vector potential and a scalar electric potential, can bring, in fact, for instance, you to a system of equations, which you can see at the bottom of this slide. Then, of course, you have the coupling with heat transfer, which takes place, and so the temperature evolution, which is going, in fact, to be piloted, in fact, by the heat transfer equation. So the heat transfer equation, where you have a rho c, which is the specific heat, K, which stands for the thermal conductivity, and the source term, QEM, due, in fact, to the local heat rate generated by the eddy current, in fact, through the Joule effect. And so, for instance, if you use an AV formulation, you have a simple expression for the QEM, which can be accessed by the integral over 0 to t, t being the period of the input current, of sigma times the derivative of A with respect to t. Okay. So now we have spoken a little bit about the physical models. There are also some solid mechanics and metallurgical models, but I will not go into detail of this today. So regarding computational modeling, one thing, in fact, you need to know about this is that you have really, regarding space discretization for electromagnetic modeling, you really have basically two kinds of approaches. You have one approach in which, in fact, you are going to use coupled boundary elements and finite elements, meaning that in literature those days, most of the computations in the inductors and the workpieces are done through finite elements. However, there are two approaches when you deal, in fact, with the coupling between both of them. One approach, in fact, is to use boundary elements to couple inductors and the workpiece. And so this can be done, in fact, so you see, for instance, in this case, where you have, in fact, the inductor and the workpiece, which is being heat treated. And so you are going to use boundary elements, which are going to be based on the surfaces of the finite elements mesh. And through this, in fact, we create a system which couples both of them, and which can be a first approach for coupling. And the second approach, which you find in literature, and which I believe, in fact, is more efficient in terms of computational modeling in reducing computational time, is to mesh, in fact, the surrounding air for the inductor and the workpiece. So here again, if I have a look, so we have the inductor and the workpiece. So you see that you mesh them exactly as we did in the previous slide. However, afterwards, what you do is that you create a box, an air box, in fact, which surrounds and embeds, in fact, both the inductor and the workpiece. And it's in this box that you are going to do the electromagnetic computation using finite elements in the air. And this can be quite efficient, especially when afterwards you want to try to use, for instance, parallel computation techniques. Okay. So another thing, in fact, which you need to know when modeling electromagnetic problems for solid-state forming processes, you basically have two kinds of elements. You have what I call, I would say, classical nodal elements, in which the unknowns are the values of the field at the nodes. For instance, I have shown here a 3D P1 tetrahedron, in which the unknowns will be located at the nodes of the tetrahedron. And you also have the edge elements, developed, for instance, by Bossavit and Nedelec, in which the unknowns are the trace, in fact, of the field on the edges of the finite element. And so this, in fact, is what, in fact, mostly can be used for electromagnetic computation. Why do we use those elements? Because they are more adapted, because they only enforce tangential continuity of the field. You know that in electromagnetism, the fields have only, for example, the H field has only a tangential continuity and not a normal continuity. However, if you use classical nodal elements, you enforce a normal continuity which is not physical and which very often can give rise, in fact, to some spurious oscillations in the numerical solutions. And therefore, that's why it's better, in fact, to use edge elements. Okay. And so, for instance, you have some codes, different codes, in which, in fact, you have an approach in which when you use finite elements, you have the same geometrical support. So, for instance, here a tetrahedral support, but it could be hexahedral or prisms if you use speaking about 3D elements, in which, for instance, you are going to solve the physical problems different from electromagnetism, such as heat transfer, solid mechanics. You are going to solve them with the finite element, the nodal version of the finite element. And you are going to use the same geometrical support, however, with a different kind of interpolation for electromagnetism, as you are going to be using edge finite elements. So I have spoken now about space discretization. Now let us speak about time discretization. Here again, there are two different choices which you can have. So the first choice, which is often used in software, modeling software, is the choice of full-time integration. Why? Because for general cases, in fact, when you have either non-periodic input currents or nonlinear magnetic materials, in fact, you are going to solve the system, for instance, if you use AV formulation, which I showed previously, the system, in fact, evolutions are going for A, depending on the location and the time, You are going to solve it at each time step, so you are going to discretize the period of the input current with 32 or 64 time steps, and then you are going to do an integration scheme at each time step to access the value at the next time step. And so this, of course, is the most general case, and so it works in every case. However, it can be quite time-consuming, and so that's why, in fact, in some specific cases, you can use what is called a harmonic approach, meaning that if you have sinusoidal input currents, and if you have linear magnetic materials, you can transform your system, for instance, the AV system, which I showed here, you can transform it in a complex system, meaning that you are going, in fact, to express A as AX times an exponential of I omega t. And so this, in fact, means that you are going to solve a complex system. So it's the system which is denoted just below. But of course, it's a larger system than the one you use for time integration. However, the big advantage is that you only solve it once. So, and this is why, in fact, in some modeling software, you are going to be able to use a harmonic approach if you are in this specific case. So now, in fact, regarding, in fact, the strategy, so we are, in fact, facing multi-physics problem, and so you can have different kinds of coupling strategy. So here, in fact, I'm just giving a few examples of coupling strategies we can be used. So for instance, regarding, in fact, first, a loose coupling strategy for induction heating. So what does it mean in that case? It means that we are going, in fact, to solve the electromagnetic field problem over, in fact, a full period, okay? And so, for instance, trying to access the joule power. And if once, in fact, we see, and this is done on the, you can see this on the right-hand side, if we have converged between two periods over the electromagnetic heat source term, then we consider that, okay, we have converged, and so we move to the heat transfer computation, and we do heat transfer computation as long as the electromagnetic parameters have not changed too much with respect to temperature. But as soon as either the electrical conductivity or the magnetic permeability has changed, then this means that, okay, we need to redo electromagnetic computation and try to converge over new joule power, and then we go on to the heat transfer computation. So this is, I would say, the weakest kind of coupling strategy which can be used for induction heating. Okay, so this in fact, okay. So now what we call a weak coupling strategy, for instance, for magnetic pulse forming, this is a bit different. It means that, in fact, in that case, we are going to solve at each time step both the electromagnetic computation and then the solid mechanics computation, because you have some deformation which takes place, and also the heat transfer computation. And so then we are going, in fact, to model at each time step all those problems to solve them, but we do it only once, meaning that we do not try to be consistent at each time step between the electromagnetic problem, solid mechanics, and the heat transfer. And so we do this, in fact, until the end of the time steps. And another example of stronger coupling strategy, so still speaking about magnetic pulse forming, is, in fact, to do at each time steps to do iteration to between the three types of computation: electromagnetic, solid mechanics, and heat transfer computation. And so to run them until we have converged both of the electromagnetic fields and the displacement field. And once we have converged, which can be done, for instance, through a fixed point approach, then we move to the next time step. Of course, the stronger the coupling strategy, the more it will cost in terms of CPU time at each time step. However, you are sure to be more accurate and not, I would say, to start adding some errors at each time step, which can lead in the end to a quite inaccurate result. Okay. So one thing also you really need to pay attention to when you are doing modeling for electromagnetic coupled problem, of course, It's the skin depth effect, because you know that, okay, as you can see here, you know that the classical skin depth effect, in which, in fact, you know that eddy currents are going to concentrate in the area which is located under the surface and are going to decrease from the surface when you move inside with an exponential of minus x over delta, where the delta, in fact, is the skin depth area. And this skin depth area, of course, gets even smaller when you increase the frequency, as in heat treatment application, or when you increase the electrical conductivity of the magnetic permeability. And so, for instance, when you do, and so you need, of course, to mesh accurately in the skin depth area. For instance, okay, when you have non-magnetic materials or ferromagnetic materials, you see that for a given, when you have a look at the magnetic field lines, you see that, of course, when you have a ferromagnetic material, for the same frequency, the magnetic field lines will tend to concentrate underneath the surface. And so this is a simple axisymmetrical case of induction heating. But however, you see that you really need to have a mesh which needs to be quite fine in the area which is being heat treated. So another thing also which is quite important is to try to reduce the computational time, because right now, for instance, when you solve coupled 3D electromagnetic and solid mechanics or heat transfer problem, you can get huge computational times. And so in order to be able to reduce them, one thing which most software do is try to use parallel computing. And so that's why, in fact, I said previously that it seems to me that finite element approach, the global finite element approach for space discretization, is much more adapted for parallel computing than the approach using boundary elements. Because there, for instance, you can use mesh partitioning algorithms and having algorithms which are going, in fact, to try to get you roughly the same equivalent number of elements on each submesh. And also, you are going to try to minimize the interface size between the submesh. Why? Because this is in order to minimize the cost of interprocessor communications. And so, for instance, here, sorry, I don't see the next slide. Okay, it's good. Okay. No, okay. Since a 2D example, which okay, so okay, no, so I'm just reconnecting. Okay, just one moment. Okay, I'm just reconnecting. Okay. Okay, so now it's working. Okay, good. So, for instance, regarding computational time reduction, so the example I show is, in fact, okay, so for a 2D application where you see, in fact, you imagine an inductor which is embedded in the air domain and a workpiece. And so, in fact, we kind of partition the domain between different meshes, as you can see. And so, for instance, and so then each mesh is run on one processor, and afterwards the parallel computation iterates until, in fact, you get the result. So, for solid state powering processes, so for instance, modeling magnetic pulse welding processes. So magnetic pulse welding is used, for instance, to weld unweldable materials, unweldable by classical processes. And so, for instance, the idea is to try to determine impact velocities and residual stresses in order to enhance the welding quality. And so here, in fact, you have a view, in fact, of a welding application in which you are going to have a part, in fact, which is going to be magnetically pulsed toward the other part, and this is going to make the welding. Okay. Okay, so I don't have, in fact, the animation for this. Okay, so just, in fact, the remeshing, so in fact, Just this is to have your attention on the remeshing, which is quite complex here, because since you are deforming the part in the air, you have to remesh the air. And so, for instance, you have to develop some specific strategy in order to try to redistribute the deformation of elements towards further elements, in order, in fact, to preserve a good quality, a good average quality for the finite elements. Okay. So, yes, before there was an animation, but I think, okay, has a problem running the animation. Okay, so let's go. So, for instance, what you see is that you can get, in fact, some supersonic velocities in a few microseconds. So you have here, in fact, you see that you can reach, okay, values of 1,000 meters per second. And you see also that with those computations, which we have done here at CMF, you can also access the residual stresses, which will, and those, of course, are very important because they will contribute to holding both parts together. Right? Okay, so this is an example of application for magnetic pulse welding. Another application regarding induction heat treatment processes for crankshaft. So in fact, here in fact, so I'm sorry, okay, normally, okay, there were some animations also, but okay. So in fact, because in those processes, in fact, you have an inductor which in fact is moving around the crankshaft in order, in fact, to heat treat the crankshaft. So normally there's an animation showing the rotation. Okay, so I'm sorry. In fact, okay, we cannot see the visualization, but we can compute, in fact, the temperature evolution, the metallurgical evolution, because of course you need to see how the part is going to oscillate. And you can also access, for instance, the distortions which can appear during quenching. And so this is quite important, for instance, because afterwards those distortions, you will try with the software, in fact, to try to control them and to minimize them in order, in fact, to be able to have parts as close as possible to what they should nominally be. Another thing, in fact, I wanted to speak about is about EPM, so for solid state, but about process design and optimization. So when we speak about process design optimization, so this means that we're going, in fact, to try to achieve some objectives set by the industrial end users, for instance, such as minimizing strain and stresses, or reaching a global homogeneous temperature field, or prescribing temperature evolution in some areas of a workpiece. And this being done through various, of course, control parameters, which are either the power input, the frequency, the electrical input, circuit design. And so, of course, when you do process design, it requires efficient numerical modeling because, as I said previously, the direct numerical electromagnetic couple problem can already be quite expensive in terms of CPU time. And so you need, in fact, to have some specifically designed algorithms and some parallel computation in order to be able to get your results in a quite reasonable time. But another thing is that also your design objectives need to be formalized into cost functions. And so it will be able, in fact, to use optimization algorithms. And so, for instance, so I'm not going into too much detail mathematically speaking, but however, okay. When, for instance, mass heating, we can try to minimize, I would say, the temperature, the difference between the temperature at the end, final time, and an optimal temperature, and to minimize, in fact, the integral of the square of this difference over the domain. So this can be an objective in terms of optimization. In heat treatment, for instance, we can have another objective, which is to try to minimize the difference between those temperatures over the domain, but also in terms of time at each time during the whole duration of the process. I will show an example of this. And so then you are going to say, okay, my optimization problem is try to find some optimum parameters, let's call them U, such that, in fact, your cost function is going to be minimized. And so, you know, okay, there are two main kinds of algorithms when you speak about optimization. So you either have gradient algorithms or non-gradient algorithms. Non-gradient algorithms including evolutionary approaches, genetic evolution strategy algorithms, which are more adapted, in fact, when you want to reach global minimums. And so the key point, in fact, for a good optimization is to have, in fact, an efficient and robust direct model, to have, of course, a representative cost function, and to search intervals, in fact, as specific as possible, and, of course, to formalize the constraints you have on the process parameters. So, for instance, the non-gradient approaches, they are often approaches which are assisted by what we call a meta-model. Meta-model, in fact, is a kind of reduced model which gives you results quite close to your direct finite element model. And so in those cases, in fact, what we can do, for instance, what we do here in CMF, is try, in fact, to have an efficient mapping of the objective function with a sort of Kreyszig procedure. And so we are going, in fact, to use those approaches coupled, in fact, with a parallel strategy in order, in fact, to be able to converge towards a minimum. And so you see, in fact, in this slide, the kind of approach. So you initialize with n finite element computation, meaning n runs of the direct finite element model. And so you then get a database. And so you use an explorer and a calculation manager. And so all this can be done in parallel, which is quite important to try to reduce the CPU time. And so just an example of application here, in fact, the idea was to try to optimize power density distribution for the heating, in fact, of a shaft head. So the two parameters, in fact, here we were aiming at optimizing were the current density and the frequency. And so, in fact, this has been done, in fact, so with those approaches. And so, for instance, what you see is that with about 216 finite element computations, we have reached, in fact, a quite close, we have almost completed our objective in trying, in fact, to reach the optimal power density distribution which we were aiming at. Okay. And so another kind of approach, in fact, is to try, in fact, to use gradient approaches. So the gradient approaches, in fact, so this, in fact, in those approaches we use gradient algorithms, meaning that we are at each, in fact, iteration, we are going to determine the gradient through some discretization approach and try, in fact, to compute the sensitivity and then to go on minimizing the cost function. And so here, in fact, I show an application for an induction heat treatment case. So in this case, in fact, what you have is that you have an inductor which moves, in fact, parallel, in fact, to a part which is being heat treated. And so here, in fact, what we did, the idea was, in fact, to try to control the temperature evolutions close to the surface as closely as possible. And so to optimize the parameters we had to optimize here were the current density, the frequency, and the inductor velocity. So here, in fact, what you see, so if you have a look at the temperature, which are shown, in fact, on the bottom of the slide, you see that the temperature in the area close to the surface follow a given path, which is the path, in fact, which was aimed at by the industrial, in fact, which wanted to heat treat his parts. And so you see, in fact, that we have converged in that case in about 10 iterations. You have, in fact, the frequency and the current density, which we were not very far from the optimal one, but still. And so you see that about 10 iterations, we managed to converge on both of them. And when you have a look at the top on the right-hand side, you see the decrease of the cost function over the 9 iterations. Okay, so just to show that, in fact, gradient approaches can be quite, in fact, efficient if you start from a given set of initial parameters which are not very far from the optimal parameters. And so this is why it's often quite interesting, in fact, to couple, I would say, algorithms such as the one I presented previously, so non-gradient algorithms, to try, in fact, to reach already the part of this parameter space where you can find the optimal parameters, and then to use gradient approaches to refine. Okay. Okay, so in fact, and so, well, we have already reached the conclusion. So just to say that, okay, right now, okay, what you need to know is that, okay, several computational tools, I would say, are now available to model electromagnetic coupled problems for solid-state EPM manufacturing processes. Those tools are based on the different kind of features, so regarding space discretization, finite elements or boundary elements, regarding time discretization, either full-time integration or harmonic approaches. And those tools, most of those tools now have parallel versions in order, in fact, to reduce computational time. And those tools now, I would say, can be coupled with optimization techniques in order, in fact, to improve process design. And so I would say some directions, in fact, for research, which I believe are interesting. So first of all, I would say to try to develop, I would say, more efficient solvers for linear systems arising from harmonic approximation, meaning when I spoke about harmonic approximation, I said, okay, we are led to solve large complex systems. We solve them only once, but we have to solve them. And very often, those systems are very poorly conditioned, meaning that, okay, it can take a long, long time to try to reach a solution. And sometimes even so this means that you need to have very good preconditioning techniques for those systems. And so, for instance, some people are working, for example, using multi-grid preconditioning in order, in fact, to be able to get better conditioning for those systems. Another thing, in fact, which is important is to use intensively parallel strategies, because right now, or very often when you deal with 3D modeling of electromagnetic coupled problem, you still get very high computational times, which makes sometimes, I would say, the use of modeling quite expensive, and not always, I would say, because industrials very often want to have a quick response. However, they do not get this response early enough, and so sometimes they do not use as much as they should modeling strategies, computation. And so parallel strategies are also a field of research which is still quite important right now. You also have, I didn't speak in fact about in this presentation about coupling with electrical circuit modeling. However, this is something which needs to be done because in fact very often, for instance, in numerical models, the kind of input parameters you have will be the current density or the voltage. However, for instance, often industrials have access either to the power which they can feed into the system. And so if you want, in fact, to be able to pilot your process through the power, this means that you have, in fact, to model the electrical circuit between, I would say, the mains where your system is going to be electrically fed and your induction or your magnetic pulse forming. So this coupling with an efficient electrical circuit modeling is important. And also, I believe that setting up new optimization approaches is quite important. In fact, coupling, I would say, zero order, meaning non-gradient and gradient algorithms is, in my opinion, very important, in fact, to try to really make the most out of modeling, in fact, in order to improve process design. Okay, so I will stop here for the time being. Maybe it was a little bit quicker, but okay, since the animation I had before did not work, so okay, this is why, okay, I know that a little bit shorter. So thank you for your attention, and if there are any questions, I will be glad to answer your questions.